Welcome to the webinar on improving chip reliability through synchronizer optimization. I'm Jerry Cox. Thank you for signing up for the webinar. Please enter your questions in the question window. You can do that at any time. I will ask the speakers to address the urgent questions as we go along. The others we'll do at the end. I'm going to give a brief introduction of our panel, and then we'll have our keynote speaker introduce synchronizers and suggest where they are likely to be found. The most common measure of synchronizer reliability is the mean time between failures, MTBF. As our tool designer will explain, automatic simulation of a synchronizer's behavior is the best way to determine MTBF. We have on tap a demonstration of a public synchronizer, one which you can download along with a tool to measure MTBF. A question and answer session will wrap up the webinar. I got my degrees at MIT and EE. Later, I became chair of the computer science department at Washington University. I founded Growth Networks 18 years ago and recently started Blendics. The first one got sold to Cisco, and the second one brings you today's talk. Shlomi Beer received his doctorate in electrical engineering from the Technion in Israel, and he's written a string of very important papers on synchronizers and metastability. Dave Czar received his EE and CS degrees from Washington University and is the designer of the EDA tool he will be demonstrating today. Tom Cheney received his EE degrees from K-State and Washington University, and we can answer your questions about the history of metastability as well as those on metastability measurement techniques. He captured the first images of a flip-flop going metastable just about 50 years ago. So, Shlomi, please take it away.
Thank you, Jerry. Yes. So to start talking about synchronizers, we actually synchronizers can be found in any modern chip, as the one you see in the picture. The main reason for that is today design styling is to break the different clock domains in different small pieces, where each module operates at a different clock or maybe also voltage. And in order to communicate, those modules need to send signals between one clock domain to the other, so synchronization is needed. And the most common form of synchronization is a couple of concatenated synchronizers, as you will probably know. And a common example for that, it's an example of the communication controller you can see in the picture, where you have different memory controllers to different memory interfaces. You have CPUs and maybe another accelerators or DSPs in between each one, operating at a different frequency. And the number of synchronizers increase with the technology node because that reason that today in different integrated circuits you will find more different islands of different frequency clock domains, and the communications between them also increase. So one of the forms to evaluate the reliability of that synchronization interfaces is to evaluate the mean time between failure, which is the most common measure to evaluate the probability of failure of such communication. So as you see in the the slide, the mean time between failure can be evaluated basically by 5 parameters. 3 what we call the extrinsic parameters that are system dependent, and 2 intrinsic. So these system parameters are basically the frequencies of the two sides, the sender of the signal and the receiver, while the other one is the allotted time for resolution, which is actually a direct function of the number of flip-flops of the synchronizer used for synchronization. The two intrinsic parameters are actually dependent only on the circuit of the flip-flops used and are not system dependent. We call them, one it's the resolution time constant tau, and the second one it's the metastability window you see in blue. So let's take an example on how these calculations can be done for a real circuit. So we take an interface between a 50 megahertz clock and a 500 megahertz clock, and we take, for example, in this case, one synchronizer having some tau and TW, and we took two synchronizers, one having a tau of 100 picoseconds and TW of 80, while the other have half the resolution time constant. So in one case, when we come and do the calculation, we end up with a mean time between failures of 5 minutes, which is basically very unreliable. While the second one has a very high MTBF of thousands or hundreds of thousands of years, which is obviously very reliable. And these examples only shows you the importance of evaluating correctly the tau of the synchronizer you are using. So on what the resolution time constant depends. So we have divided this dependence in 3 big different categories: the circuit, process, and operating conditions categories. While in the circuit, we list different type of architectures of the flip-flops, while they have built-in self-test, reset, the sizing of the transistors, routing, and the number of stages, obviously. In the process side, we can list which process node are those circuits built, the process flavor, threshold voltages, and also how we translate process variations into the calculations. And in the operating conditions, this is actually mostly the voltage, supply voltage, duty cycle, and temperature. So just going on the influence of some of those, one important thing is the technology node. So in some research we have done, we have seen that the resolution time constant does not necessarily decrease with the technology node. So actually relying only on the technology node shrinking for having lower resolution time constants, it's not completely reliable. And we have seen some inflection points for different flavors where the tau gets bigger even when the technology scales down. This is particularly important because one could have thought that only by reducing the technology node, the resolution time constant will decrease because of an intrinsic time of the circuit, but that is not always the case, and we should evaluate that in any case specifically. A second important thing to take into account, it's the supply voltage and temperature, which we are showing you here some actual simulations of a real circuit, real synchronizer, where you can see the huge difference between like nominal conditions, which will end up in some point here in the middle for the supply voltage and temperature, while when reducing the supply voltage or decreasing temperature, the resolution time constant goes to very high values. So that's also something very important that to take into consideration when designing or when evaluating different flip-flops. Then we have also process flavors, which in today's technology you can find like many of them, like high power, nominal, low power, high performance, etc. Each process has its own naming conventions, but the point is that tau gets increased when moving from the high performances towards the low power. That's mainly because of the change of the VT. So you see that on the right table, that we have influence both on the process flavor going from HP to LP, and also when changing the different thresholds of the transistor you're using for the flip-flops, from low VT, standard VT, and HVT. So if we take as reference the low VT with high performance, which has the highest resolution time constant, then for the low power HVT transistor, you will have like 10 times a higher tau that, as you saw in the example, can lead to extremely high mean time between failures. That's for this case. And for the last thing I want to talk about now, it's about the importance of evaluating what we call tau effective. So in the formula for the mean time between failures, we have talked about the resolution time constant, but the actual thing is that this tau, it's a composition of the master and the slave resolution time constant, as you can see it on the formula on the upper part. And the combination between the two is an harmonic combination, which alpha being the duty cycle of the clock used. So duty cycle has importance. In here, in the case where the tau master and tau slave are the same, so we have one only tau that it will be equal to tau master and tau slave because they're the same. But when we have differences, and that are most of the cases between the resolution time constant between the master and the slave composing the flip-flop, knowing the duty cycle or playing with the duty cycle can change as you see it in the different cases in the graph. So depending whether tau master is higher or lower than the slave one. Okay. So, Dave, I will pass it to you now.
Great. Thanks, Shlomi. So this is Dave's R now, and as Shlomi has discussed, right, finding MTBF for a synchronizer requires knowing tau and TW. And of these, tau is the most important to get right, as it's in the exponent of the MTBF equation. Yet it's not so easy to determine. There's the issue of the effective tau, that Shlomi just discussed for master-slave type circuits, process variability, design choices, and so on. It seems that simulation is the only reasonable way to determine tau with any hope of finding the worst case, which is what you really need to determine if your synchronizer will stand up to the environment in which you plan to use it. To make things simple for discussion here, let's consider a prototypical master-slave E flip-flop like this one. We want to simulate the circuit using SPICE, for example, and see what happens to Q as it resolves from metastable state. So we need to get the device into metastability and then see how it resolves. Let's consider the slave. So a common way in the literature and also in practice from talking to many people over the years of driving this to metastability is to use the shorting nodes method. This method takes the feedback paths of the latch and shorts them together at time 0 in the simulation, sets an initial voltage on them to be a metastable voltage, soon to be around half the ED typically. And this is shown here with this line between nodes V1 and V2. We can remove the short at some time after time 0 and see how it resolves from that initial condition. While the circuit does do something when you do this, it does not show you what happens as the latch exits metastability for any real circuit I've ever seen. Obviously, the initial state is V1 equals V2, which is not going to be the case during metastability unless you have a perfect symmetry in your circuit. Same inverters, same loads, same variability of parameters, and so on. So since V1 does not equal V2 at a true metastable point in the circuit, you'll get an inaccurate estimate of tau. The only way to really see what happens when the latch exits metastability is to adjust the D to clock timing to force Q to go metastable. The result of doing this is shown here. It's tricky to make SPICE do this. An arbitrarily long metastable time is shown, but it can be done. You can clearly see that the metastable voltage, Vm, is not 1/2 VDD. VDD is 1 in this case, and the metastable voltage here is about 440 millivolts. If you were to look at both V1 and V2 nodes, you'd see that they differ by about 10 millivolts as well. The outputs in this case, there's 20 of them, are showing different resolution times based on slightly different D to clock input timing. Since it's tricky to run simulations to get plots that look like this, several hundred simulations needed to be run, extracting information from earlier simulations to set up the later ones. A tool is useful to automate this process. MetaACE is such a tool that uses your extracted SPICE netlist plus a little wrapper to simulate the report tau and TW, so you can do accurate MTBF calculations. The wrapper that you need to add is minimal, and I won't get into a lot of details here. If we have examples you can download. In fact, we make a limited version of MetaACE available for free download to anyone who wants to analyze their own synchronizer circuits, work on improving them, or just to learn more about metastability by playing with some of our sample public synchronizer circuits. The free version only limits you to 250 nodes that can be in the circuit to be analyzed. We found this is more than enough to simulate a reasonable synchronizer circuit with a C-only extraction, which we've also found is about 5 to 10% off of a fully extracted netlist in practice. So it gives you a pretty good idea of the ultimate performance, but with a significantly reduced runtime due to the much smaller circuit size that needs to be simulated. So let's take a quick look at how MetaACE works. The simulation of the C-only extracted netlist for this circuit takes about 10 minutes to complete with MetaACE. Most of that is doing SPICE simulations, so I captured a video of it, and that's what I'm going to show you here. So we don't have to sit through 10 minutes of this running. Okay, I'm going to talk about the UI functions and such as this example runs. The circuit we're going to use that this is simulating is this more complete circuit, which is also available, as Jerry mentioned, and we'll give you links to that at the end. The MetaACE GUI allows you to specify your netlist, right? The SPICE simulator, you can specify VDD and temperature, as well as the input-output you wish to simulate. Assuming that you set up your netlist properly, all you need to do is press run after entering that information, and MetaACE does the rest. So I'm going to start running the video. And the first thing that you'll see happening is me loading a configuration file that I had saved earlier. All the parameters that you see can be saved to a file for later use in the GUI or from the command line. In this way, you can set up a simulation and then make modifications to your circuit, like changing the process or flavor of transistor used, or even a completely new circuit design, and see how that affects tau. You can sweep voltage and temperature over whatever range you want. This example is just doing a fixed voltage and temperature, however. If you sweep, MetaACE will produce a CSV file for all the results that you can directly load into Excel, MATLAB, or other analysis tool. As MetaACE is running, it's showing output plots so you can watch the progress, and also so you can see that everything's looking okay. On the left side, we're seeing the overall view from the start of simulation. We're looking at two different nodes here. We're looking at the output of the slave on the bottom, the output of the master on the top. So this is showing you from the beginning of simulation, you see a rising clock, you see the masters starting to go metastable. The slave isn't doing anything very interesting here, it's essentially just filtering the master at this point. What we need to do in the simulation is force the master's metastable voltages towards the falling edge of clock so that it starts to affect the slave. So when the falling edge of the clock happens, the slave captures an invalid D to clock transition. That will force the slave to go metastable, and then we can measure the slave tau and TW. So this is where having the video is helpful, right? It's about 3 times, I think I said 3 times actual speed. So in just another moment or so, we should see the master being pushed close to that edge of the falling clock, and then the slave will start to do something interesting. As this is running, we're getting some status updates, in this progress window, and it's showing us, what times we're doing simulations and such. Again, this is just to see that things are progressing. As you see here, you see the slave has now started to do something interesting on at least one of its traces. On the left side, we show just the last resolving high and the last resolving low trace, so it doesn't get too busy. On the right side, we have a zoomed-in view of what's happening at that metastability point. So here you can clearly see the slave starting to do some interesting things. Note that the master, it's the transition high here that appears to be making the slave go metastable. Not much will happen interesting at the time when the slave is metastable now, since all the interesting things to the master occurred pretty much before the clock. So after the slave starts to go metastable, we'll drive it metastable for a long time to get past any transients of the circuit. So notice as it entered metastability, there was this little hump. We want to get past that. We want to drive the output metastable for a fairly long time so we can take accurate measurements of what happens as it exits metastability. After converging a determination of tau, the simulator will automatically stop and report the final values. The values can then be used to calculate MTBF. The MetaACE will also do a quick computation of MTBF for you, as we'll see in a moment, based on these parameters that I've entered down here. So I can give it a sample data rate, sample clock rate, and a settling time, for example, and it will do an MTBF calculation for me. This is not taking into account tau effective, however. It's just a rough estimate. So this is what it looks like at the end of the simulation. At this point, we've got our tau. We can then make changes to the circuit. We can rerun the simulation and see if those changes affected tau in a positive or negative way, for example. Okay. This also produces a CSV file, even if it's just one example. So you can extract all the data in an automated way. So just to recap the advantages of MetaACE, it can easily determine tau and TW for you based on running simulations that accurately reflect actual circuit behavior. It can sweep voltage and temperature for you, supports any circuit that you have a SPICE netlist for. You can run it from the command line. It's also been verified against silicon with work we did with Technion several years ago. There's a paper on that we can refer you to if interested. I want to thank you for taking the time to walk through this demo with us and see how easy it can be to analyze metastability in your own circuits. And I'd like to just point out, so that here on this slide, we've got some references to papers on metastability, more depth information, and I mentioned the limited version of MetaACE. You can find that at the MetaACE link there, and the public synchronizer that I used is available as well from the URL that's there in addition.
Thank you very much, both Shlomi and Dave. We've got a couple questions that we'll now see if we can get some answers to. First, I think this one I'll address to Shlomi. The question is, so how do I compute my effective tau if I have a master-slave flip-flop? I was only given tau by my cell provider, so is that tau effective, or is that something else? Shlomi, you got anything to say about that?
Yes. Yeah, that's a good question. So probably if you get your tau by the cell provider, a good question to ask will be whether this was simulated or measured for the master or the slave. I doubt if it's a tau effective, but the most probable thing is that's the tau of the slave. That's a common mistake to measure either one of them or the master or the slave. So if if you had one of them and you can make sure which one of them is, but you don't have the other one, so let's say you have the tau of master but don't have the tau of slave, looking onto the circuit can give you some perspective whether they will be different or the same. And then a good point to evaluate that will be just using some of the graphs I showed in my slide to see whether how worse condition that will cause to the circuit when you calculate the tau effective that you will really have in that flip-flop. The best way on the other side will be to take the cell circuit and just simulate it using MetaACE, for example. In that way, you will be able to get a tau effective in a reliable way.
Okay. Here's one for you, Dave. Can you give an example of how I might use MetaACE to design a better synchronizer flip-flop?
Sure. You run it, get a result, and change something. That's the high level. One of the reasons that we developed MetaACE in the first place was to sort of look at those kinds of situations. If you have a circuit, you can give a flip-flop that you intend to use as a synchronizer. You can simulate it. You can find out if you've got good performance or not based on your needs. You can then do things to change the circuit. You can change, for example, the threshold voltage of the transistors you're using. You could change the voltage. You could change the process node. You could redesign the circuit, trying to make it more effective, reducing load and internal nodes and so on. And when you do those things, simply re-extract the circuit and run the exact same simulation on it again. It may take on a fully extracted netlist, a couple of hours, but on the C extractions, it takes about 10 to 15 minutes to run a single stage flip-flop. So you can get results very quickly about if your design changes are affecting tau in a positive or negative way.
Okay, and here's another question. How do I use your tool to calculate MTBF for a synchronizer in an FPGA, Dave?
Well, if you're lucky enough to work at the FPGA vendor, then you can actually simulate the circuit. What MetaACE requires is running SPICE simulations. So you need to have an extracted SPICE netlist, and you also need to have the foundry models based for the process that that circuit is being implemented in. If you're a user of an FPGA and all you're given is the design tools from the vendor, then you're not going to be able to use MetaACE to simulate those circuits. So you have to go back to your FPGA vendor and beat them over the head to say, I need taus or tau effectives, and go read some papers and learn how to do this.
Okay, I've got another question. Can MetaACE be used on circuits other than synchronizers which display metastability? I think I can answer that one, and the answer is yes. For example, for arbiters, MetaACE works just fine as long as you have the ingredients that Dave just mentioned. So I'm going to go on to another question now. How do I use MetaACE to compute tau effective? I'll let Dave answer that one.
So as Shlomi talked about, right, tau effective is really the combination of tau master and tau for the slave. So if you have a master-slave flip-flop, for example, you want to use MetaACE to simulate the master, which you can do. It has several parameters. When you specify the clock, you can say it's a single-edge clock, and you want to look at an output after just a rising edge, for example. So you can look at the master latch, and you can see how it performs, get a tau for that, and then you can simulate the output for the slave, which is what I showed you. And you'll get a tau for each of those, and then based on the range of duty cycles that you think you're going to use, you can look at what the worst case tau would be based on the duty cycle and the tau that you obtain for the master and the slave. So essentially you have to run two independent simulations, one for the master, one for the slave, and then combine those results to get tau effective.
Okay, I'm going ask one more question of Dave, and that is, can I simulate multi-stage flip-flops with MetaACE?
Sure. It's only a matter of how much time you have. Obviously, 2 or 3 flip-flops in series, it takes longer. You have to drive each one metastable to force the next stage to go metastable. But there's no reason you can't do that. We've done it ourselves. That's another parameter that you give the clock. When you specify what your clock is how many clocks to the output that you need. So the signal you're looking at is at the output of the third stage of a series of flip-flops, 3 clocks to the output. You'll get yourself get yourself more than coffee, a lot of coffee. But it'll give you a result of the performance of that circuit as well.
Okay, we're running to the end of our time. I'm going to just mention a couple more questions that I think are important. One is, how do I get the public synchronizer? You go to our website, and a link will be displayed there. And how do I get MetaACE Limited? Again, go to the website, and you'll find a link there so that you can download MetaACE. So we thank you very much for attending our webinar today.